show. Beginning. Great. So for the second lecture for this week, we're going to be covering the small part of the circulation, the microcirculation, where we're actually exchanging nutrients and water and oxygen and carbon dioxide. So all of your major vessels have taken the blood there. You control it with the opening and closing of arterioles primarily to move it into the capillary beds. And now we're going to talk about what happens in the capillary beds. Toward the end of this lecture, I have a section in here on the anatomy of blood vessels. We're not going to spend much time on that today because now the way I have it set up, the blood vessel anatomy has a pretty serious lab session, and the second lab practical is mostly blood vessel anatomy. This first lab practical has very little of that on it. I'll explain to you a little bit more in an announcement about how to prepare for these first tests. But meanwhile, let's go through the rest of this circulation stuff. Okay, we've come from the aorta to the large arteries, smaller arteries, the arterioles. Once you get to the arterioles, you have first order arterioles, the very first ones. They split off, and then you have even smaller ones, and even smaller ones, and even smaller ones. And these third and fourth order arterioles actually connect to capillaries. So this one could close off a pretty large area of tissue. This one is only going to close off a small number of capillaries so that you have more precise control over blood flow through your tissues. Then you have the capillary beds where the exchange actually takes place. And then you reverse the process. Little venules, bigger ones, bigger ones, bigger ones. And then the small veins, the large veins, the vena cava, and back to the heart. So what we want to do at these tissues, at the capillary beds, is exchange nutrients and water and gas. What you have is a huge cross-sectional area. Remember that capillary beds are where you have the largest total cross-sectional area because you have billions and billions of capillaries. And these capillaries, every cell has a capillary pretty close to it because diffusion goes really fast over a small distance, but then it slows down a lot. So you don't want to have a cell over here and a capillary way over here. It would take maybe an hour for the oxygen to get there, and that's not good enough. So we have a large cross-sectional area, very thin walls that let things move across easily. Like I said, short diffusion distances by having so many capillaries. Remember, the pulsatility is dampened by the large arteries and stuff. When blood comes out of the heart, it is entirely pulsatile. It's either squeezing or it's not. So it's like turning your faucet on and off and on and off. But at the capillary beds, you want the blood to be going smoothly. You don't want it to do this, or it wouldn't spend enough time in every area for the exchange to take place. So the stretchiness of the large vessels and then their ability to recoil and keep the blood going between heartbeats. You push the blood in them, and then between heartbeats, they squeeze it on downstream. By the time you get to the capillary beds, it's continuous flow. Pulsatile in the large arteries, continuous flow by the time you get to the capillaries, so that you can have a very slow, even flow through the capillaries. Non-pulsatile or continuous. Very permeable. Your red blood cells are not only in close contact with the membranes, the cell membranes that line your epithelium that lines the capillaries, they're crammed in there, sort of. You know, they're in the larger arteries, there's lots of them bouncing around in there, but once you get to a capillary, the capillary is so small that the red blood cell, as we saw when we did the blood cells part of this course, they fold and go down the capillaries, so there's a lot of the membrane in contact with the membrane of the capillary. This makes it a really short diffusion distance for the oxygen inside the red blood cell to cross into the tissue and back. And that's why deformability is so important in red blood cells. And when they get older and become a little bit more rigid and brittle, they'll typically break apart, and the parts will get recycled in the liver. The spleen picks up used red blood cells and recycles a lot of the proteins and stuff. Okay, here we have the arterioles. Those are arteries they're showing. Then we get to the arterioles and smaller arterioles. This is simplified, of course. You have your capillary beds. You have precapillary sphincters that can open and close individual capillaries, venules, and then the veins taking the blood back. A couple of other kinds of blood vessels that are here in the microcirculation. You have what's called a medarteriole that goes all the way across and has capillaries coming off of it. So it gives you even more options for control precapillary sphincters at the beginning of every capillary so that you can open and close that capillary. This medarteriole can become a shunt vessel or a AV bypass. The serious name is anastomoses. Anastomoses are bypass shunt vessels that take the blood from the artery to the vein without exchange occurring. Well, if you close all of these precapillary sphincters, this medarteriole becomes a bypass vessel or an anastomosis. You also have some anastomoses. They're normally closed because you don't want blood to just go across and not exchange, except in emergencies when you're bleeding out and you need more blood to get back to the heart real quickly. You open your bypass vessels, you turn your medarterioles into bypass vessels, and that way you can get the blood across and back to your heart so you can send it to your brain or something that you might need. The capillary wall has a lot of ways for things to get through. Fenestrations are areas where the cell basically disappears and all you have is the cell membrane. So there's very little diffusion distance here for it to cross. Some things can cross through fenestrations. Other things, like water. Water doesn't cross membranes very well, but you have a lot of H2O-sized clefts that allow water molecules to pass back and forth as much as they want. You have vesicles. If you have something that's too big to fit through anywhere, you can take it in by endocytosis here and let it out by exocytosis over here, so you can get a larger molecule across. The basement membrane helps hold it together, but it is so porous that virtually everything can go through it. So you're controlling movement by these mechanisms in the cells. Then the junction between the two cells is a tight junction. Not terribly tight. It depends on the capillary. Some kinds of capillaries let very little stuff through, like in the blood-brain barrier, and others are pretty leaky. So another mechanism for getting substances across the membrane. Here are three different types of capillaries. Here you have the continuous capillary in the blood-brain barrier. It has really tight junctions. Makes it really hard for things to cross. It's hard for bacteria and things to cross into the cerebrospinal fluid and give you meningitis. It's a good protective mechanism. Of course, it's not 100% tight, otherwise you would never get meningitis. But it's a tight junction. It also makes it harder to get antibiotics and things like that across if you need them. A typical fenestrated capillary, like you have in your arms and legs and everywhere else, is moderately leaky and allows things to transport pretty quickly. And then a sinusoid or discontinuous capillary, the cells are so far apart that all kinds of stuff can go through. This is like you have in the liver, where you want to combine a whole bunch of things and turn them into products that your body can use. You let a lot of things move through the sinusoids. It's also the way that lymphatic system works, because it pulls debris out of your tissues, and you need to be able to get chunks back into the blood. And they won't go through these little fenestrations and things on a regular capillary, but a sinusoid capillary, like in the lymphatic system, can even take in a full-size cell, like a cancer cell. When cancer metastasizes, it doesn't immediately move into the blood. It's in the tissue. You have a cancerous tissue, so you get loose cancer cells around that initial tumor that are trying to go other places. But your lymphatic system is doing the cleaning job. It pulls the cancer cells into the lymphatic system through the lymph nodes, where your immune system tries to kill them. It's sometimes effective, often not, but at least you have a try. And so the cancer cells, that's why they wind up in lymph nodes first when your cancer metastasizes. You also can alter how tight these tight junctions are. For instance, histamine, when it's released in response to an allergic or an inflammatory thing, it uses a GQ protein, but what it causes is a signal that loosens your tight junctions and lets more stuff go through. So if you have a histamine attack, the blood vessels in your nose lose their tightness and your nose runs. The mucus that comes out of your nose when you're blowing your nose is basically plasma that has been allowed to leak out of the blood vessels that are going through your nose. Histamines have their own sets of receptors. They act a lot like other G protein type receptors. So your parasympathetic, your sympathetic nervous system, hormones, they have their own receptors that use G proteins, but histamine and adenosine and things like that act locally on your tissues have GQ proteins and GS proteins attached to them, so that your local responses can use the same strategy as your sympathetic and parasympathetic nervous systems can. Okay, so how easy is it for substances to move through capillary membranes? Water goes totally easy. There are so many water pores or clefts that water moves whenever it wants to. So we move water by osmosis. If you want more water over here, you pump some ions over here, and the osmotic pressure pulls the water across. So you don't have water pumps. You pump other stuff, and water follows by osmosis. But as a result, sorry, I have a frog in my throat. But as a result, water moves perfectly. So we give it a score of 100 or 1. Sodium chloride, when it's still sodium chloride and not sodium and chloride, which are charged particles that don't move well, the part that stays salt can move easily. Glucose moves pretty easily, although we do have glucose transporters specifically to make it move better when we need it to. Your large molecules, like your plasma proteins, don't move easily at all. Albumin is your main plasma protein, and it only moves 1,000th as easily as water does. Still, some of it leaks across, and you pull it back with your lymphatic system, so you don't lose those proteins. So the size and shape of the molecule and whether it's charged or not largely determines how easily it moves. Little teeny molecules get across as long as they're not charged. If they have a charge, the membrane resists them with its own charges, and therefore they don't move easily. So you need sodium transporters and potassium transporters and calcium transporters. Really big molecules don't move easily. Glucose is a fairly concise molecule, so it moves pretty well. It's got a ring shape. Gases move real easily because they're tiny. Just H2, things like that move across the membranes quite easily. So you don't need pumps for them. They just move down the concentration gradient. If you got a lot here and not much there, the gas is going to move in that direction. Now, what you're doing is you're moving these nutrients and gases and things across the membrane from the plasma into the interstitial fluid, which is the fluid that flows around the cells. Your cells are bathed in clear fluid, not red because it doesn't have red blood cells in it. And it is similar to plasma, except without the red blood cells. And it flows past the cells so that they are constantly being kept with, supplied with fresh nutrients, fresh oxygen, and the CO2 and waste products are removed and then put back into the bloodstream, either back into the capillary where it came from in the first place, or into the lymphatic system. If the waste products are too big, they're pulled back into the lymphatic system through those big holes in the side and taken back into the circulation that way. Most of the interstitial fluid is in a kind of a matrix like cotton that helps hold your tissues together. So your cells don't just float around in there. They're held in place by this matrix of loose fibers, areolar connective tissue and things like that. And they have little rivers or rivulets going through them that have the free fluid flowing through them and taking these substances. So we're looking end on. This is a pretty bad example, but there are all the fibers through there. And here's a rivulet, and here the free fluid is flowing. This is going toward me and away from me. So I've cut this little river in half and I'm looking in the end of it. But it's allowing the fluid to flow through this cotton matrix to take the nutrients and gases to the next cell down the line. Now here is the hardest part for most people of this lecture, and this is what causes the right amount of fluid to move out of the capillary and then back in. If too much moves out, your ankles swell up. If not enough moves out, you don't get enough nutrients out there. So somehow we have to move the fluid out of the capillary, let it wash across the cells, and then pull it back in so that your fluid balance stays the same, and yet you've delivered what you needed to and pulled back what you need to get it back into the system. There are two sets of forces that are going to move the water. One is just the blood pressure. If there's pressure inside a garden hose and you put a hole in it, the water would squirt out. That's hydrostatic pressure, it means water pressure. So your blood pressure inside the capillary is going to try to push fluid out into the tissues. Meanwhile, you have osmotic pressure in the capillary too, because you have a lot of stuff dissolved in there, and all those extra plasma proteins and things are in there. And osmosis is a pulling pressure. Remember, osmosis sucks. Okay, osmosis sucks, so it's trying to pull the fluid into the cell. Now, if the blood pressure wins, some fluid goes out. If the osmotic pressure wins, some fluid comes back in. Okay, because you're pushing and you're pulling. That would be really great if that was all there was to it, but you also have a little bit of hydrostatic pressure and osmotic pressure outside the capillary. So it's like you're trying to get a door open, and I've got a guy pushing from the inside and a guy pulling from the outside, but resisting it, I've got a guy pushing from the outside, another one pulling on the inside. And so whoever's strongest the guy pushing here and pulling here, if they win, the door opens. If the other two win, the door closes, right? Because you got some forces trying to push this way or push this way. So whoever wins the battle gets to move the fluid out or gets to pull it back in. And so this is a calculation you'll have to do on the test. I'll show you how this works. Here we have blood going in, okay? We're going to have hydrostatic pressure trying to push the fluid out. And then we're going to have osmotic pressures trying to pull in. Look, the pressure of the capillary, or PC, is higher than the oncotic pressure of the capillary. And osmosis is shown with the pi symbol. The oncotic pressure, they call it. That's easier than saying the osmotic pressure in a capillary bed. Oncotic pressure refers to the osmotic pressure in a capillary bed. So here we have the pressure inside the capillary, which is the hydrostatic or blood pressure, pushing out. It's winning now. The osmotic pressure is trying to pull it back in, but it's not as big. Therefore, at this end, you're going to have, it's called filtration. Filtration. Water filters out of the blood. Now, as you move along here, the osmotic pressure stays about the same, because you're not losing plasma proteins, but the blood pressure drops. Okay? Because blood pressure always drops as you move along the circulation. That's what keeps the blood moving in the direction it's supposed to go. So the blood pressure drops. Now the blood pressure isn't as high as the osmotic pressure, okay? The oncotic pressure. So now it sucks harder than it blows. And you wind up pulling net absorption. Absorption means it's coming back into the blood. Filtration is leaving the blood. Absorption is coming back in. So at the capillary end, where you have fresh blood that's full of oxygen and stuff, and good fresh food, you filter. So fluid goes out. At the venous end, you're causing this fluid to go out here. It kind of flows along here, washing across those cells and nourishing them. And then you get over here and you pull it back in, because now the osmotic pressures are winning. They're higher than the blood pressure. So you filter here, causes a flow across the cells, you pull it back in. You filter here, flow across the cells, and it moves back in. Look, here's a typical kind of test question thing. Okay, what do I have going on here? If I can get my cursor to show up. Where's my cursor? Come on. Come on. It doesn't want to show up. Okay, well, on the capillary end, there it is. I just saw it. Why doesn't it move? There it goes. There, finally. The capillary pressure, that's the PC. This is the pi C, the oncotic pressure in the capillary. Here, it's high at the beginning, and it drops down low at the end. It should be about 32 at this end, and it should be about 15 at this end. Oncotic pressure should be about 25 all the time. So 32 wins, but 15 loses. 32 wins, but 15 loses. Okay, well, this test question says, what's going on here? What's wrong with this person? Well, the oncotic pressure is fine, but look, the blood pressure is too high. This is hypertension. This isn't 32, it's more like 42. Okay, so it's going to push too much fluid out compared to how much it pulls back, and your ankles are going to swell up. Hypertension means high blood pressure. The capillary pressure or blood pressure is too high. Remember the 32 and the 15. The 32 and the 15. If it's really low, you won't push enough out and you'll pull too much in. and you'll start pulling fluid out of the cells, out of the interstitial fluid, and back into the bloodstream. That would be hypotension, or low blood pressure. You could also have a condition where your oncotic pressure was either too high or too low. And all you do is look at the graph and see, well, is that about 25? Is that about 32? Are you filtering about the same amount that you're pulling back? If so, it's okay. If not, it isn't. You know, this one here, this shows it to be 35, but look, you're filtering about the same amount as you're absorbing. So that's about even. That's about right. Okay? But if you have this one, I jumped over that one when I went here, the computer skipped a slide. This is about how it should be, about the same amount of absorption or filtration and absorption. 25, 35, you could say it's a tiny bit high. But I won't give you a tiny bit high on the test. If it's high, it's high. 42, a lot of filtration, not much absorption, high blood pressure, hypertension. Here's hypotension. Look, it's too low. It's like 26, 27, something like that. You're not filtering as much as you're absorbing. So now you're sucking fluid back into the blood cells, into the plasma, and dehydrating the tissues. You're taking fluid out of the tissues. Oncotic pressure looks fine. The blood pressure is just low. Hypotension. Most likely to be shock or hemorrhage. If you start bleeding out, if you cut your foot off and bleed out, the blood pressure is going to drop so much that you start pulling fluid out of the tissues, trying to keep your blood volume usable. Okay, so let's kind of do a problem here, like you're going to have with on the test. I'm going to say something like, okay, you have a point at along the capillary bed, and here are the pressures. You got blood pressure inside, oncotic pressure inside. You got blood pressure outside, you got oncotic pressure outside. Who's winning? Who's winning? There's a simple way to do this. First, you find the two guys that are trying to get the door open, to push it out. And that's going to be the blood pressure on the inside and the oncotic pressure outside in the interstitial fluid. So we do that as, see if I can make it so you can see it. It's not going to show up very well. Let me see if I've got something better to write. Yeah, here we go. Okay, we're going to have the pressure inside the capillary, the oncotic pressure in the interstitial fluid. Now, maybe you can see it. There we go. God, it's hard to do this. So much easier on the blackboard. Okay, so those are the two guys. Just think about it. One is pushing from the inside, one's pulling from the outside. They're going to be those two numbers. And then you're going to have the pressure outside and the oncotic pressure outside that are fighting these guys. So who's going to win? So you take the two guys that are trying to push it out, and let's say the pressure inside the capillary is, let's see, we're not at the very end, so I'm going to say it's 30. And the oncotic pressure in the interstitial fluid is, let's say it's 1 millimeter of mercury. So that's 31 millimeters of mercury, 31 outward millimeters. Then you add up the other two guys, which are going to be the pressure in the interstitial fluid and the oncotic pressure in the capillary. Those are the two that are trying to get it back in. It's pushing from the outside, pulling from the inside. Okay? So the let's say the oncotic pressure is 25, like it's supposed to be inside, and the pressure outside is 2 millimeters of mercury. Okay, there's a little bit of blood pressure, fluid pressure out there, but not much. So that gives you 27. Okay, see if I can get this on the screen. Okay, here we go. Okay, we got the pressure in the capillary and the oncotic pressure outside. I'll give you those two numbers. You add them up. And then the other guys that are fighting them are the pressure in the interstitial fluid, trying to push it back, and the oncotic pressure in the capillary. You add those up. So now we have 31 working in one direction. We have 27 working in the other direction. 31 minus 27 equals 4. Equals 4. So if the guys that are pushing out are more powerful than the guys pulling it back in, then you wind up with a positive number when you subtract like that. 31 is bigger than 27. So 31's winning. 31 is winning, and you have net filtration. Your net filtration pressure then is said to be 4 millimeters of mercury. Okay, what if it were the other way around, though? What if these were the forces trying to push it out, and these were the forces trying to push it in? I'll do one like that, just so it's try not to be too confusing. Okay, again, you do the outward forces first. So the pressure in the capillary and the oncotic pressure in the interstitial fluid, those are the two outward forces. Okay, let's say the pressure in the capillary is dropped down to 18, and the pressure, the oncotic pressure, let's say that's 2. Okay, that's out in the interstitial fluid, trying to pull it out. So that would equal 20. And let's say on the other forces, we still have our oncotic pressure of the capillary pulling in 25, like it always is, should always be. And the capillary pressure out there is 1. Okay? So that equals 26. So let's try this one. Here we have the pressure in the capillary. At this point in the blood vessel, the pressure in the capillary is 18 millimeters of mercury. The oncotic pressure out in the interstitial fluid is 2. So you got 20 millimeters pulling out, pushing out, pulling out. But you at the inward forces, you got still your 25 pulling in plus 1 pushing in from the outside. And you add that up and it's 26. So these guys are winning now. This must be over in the venous side where you're starting to pull fluid back in. Your net filtration pressure is minus 6 millimeters of mercury. That means you're reabsorbing. The forces that are pulling in are winning, and so you're not filtering anymore to the tune of minus 6 millimeters of mercury. If the outward forces are winning, you get a positive number. Any positive number means you're going to filter because it's bigger than the inward forces. If the inward forces are winning, you're going to get a negative number because you take the outward forces and you subtract the inward forces. And you get a negative filtration number, which means you're absorbing. You're going to have to do one of those problems on the practice, on the test, on the cardio test. So practice it some. Give yourself some numbers. Just make up numbers, okay? Numbers that are fairly close to the realistic numbers, like, 31 and 3 and 25 and 1. The outward forces minus the inward forces. If it's a positive number, you have a positive filtration. You're going to be filtering. If it's a negative number, you're going to be absorbing. Practice it. You get to use a calculator on the test. So even though these numbers you could easily do in your head, 20 minus 26 is minus 6, and I make them pretty straightforward numbers. But you'll get to use a calculator just to be comfortable and be sure about it, but practice it some so you can do this kind of problem. Now, what's important about this, and this is not just some kind of stupid thing that physio professors make you do, this is important because people have high blood pressure and low blood pressure. People have conditions where their plasma oncotic pressures go up or down because they have too many or too few proteins. And it causes them to fill their ankles up with fluid so they swell up like mad or become dehydrated. These things happen all the time. And these are the same forces that are going to move fluid in and out of our kidneys to form urine. So understanding the pushing forces and the pulling forces and how they affect fluid movement is critical to keeping people healthy. Now, there's one more thing that goes along with this, and that is that when you filter fluid at the capillary end with positive filtration pressures, and then you absorb at the venous end with negative filtration pressures, you don't pull 100% of the fluid back because there are some big chunks of debris that you need to get out of that tissue. And if you pull all the fluid back in, they're just going to build up and concentrate in there and cause you problems. So what you do is you filter you filter whatever fluid you're going to filter. You reabsorb most of it. The rest is kind of a thick mess that is filled with these bigger pieces of debris and whatever, and it gets pulled into the lymphatic system. About 10% of the fluid that gets filtered, instead of getting pulled back into the blood, gets pulled into the lymphatic system. So you regain all of it, but the lymphatic system serves as the vacuum cleaner to clean out the excess fluid, but also the excess debris that's left over from your metabolic processes inside your cells. So you have lymph capillaries and lymph vessels everywhere you have regular vessels. If you have an artery and a vein, you're going to have a lymphatic vessel because where it delivers fluid and brings it back, you're going to need a lymphatic vessel to bring back the excess with everything else. So 3 liters per day of that filtered fluid that doesn't make it back into the capillaries gets pulled into the lymphatic system. That's a lot. It's a big deal. Now, these lymphatic system doesn't have an extra heart pumping it around, so the movement of lymph is really slow. It might take an hour for the fluid to get from your ankle back up in the subclavian arteries. Here is where it finally dumps back into your general circulation to go to the liver and get recycled, get cleaned out, and be used again as part of your blood. So you're pulling fluid slowly out of these through these lymphatic tissues. Mostly it moves when you walk around and squeeze on them. They have one-way valves like veins do. It's generally sending the lymph through lymph nodes, especially in the groin, around the digestive tract, in the armpits, around the breasts, a lot of lymph nodes around here. This is why they detect metastasized breast cancer by looking in the lymph nodes and see if any cancer cells are showing up there. And then it finally dumps that fluid into the subclavian arteries. Now, the lymph system is a big part of your defense in your immune system. The B and T lymphocytes, all of those B and T lymphocytes that we were talking about before, reside in lymph nodes. Not all of them. Some of them are always circulating through the blood, but most of them are in the lymphatic system. That's why they're called lymphocytes. to be released or activated when you have an infection of some kind. So the blood gets filtered through the lymph nodes. It gets attacked by T and B cells. It can signal the T and B cells to be released into the blood to go to the site of the infection and attack the bad guys or whatever. Also, we'll find when we get to the digestive tract that it will transport your fat nutrients, your digested lipids. But we'll talk about that part of it later. So here we have another version of our capillary vein end, our artery and venous end of the capillary bed. You filter, you reabsorb, about 10% of it gets pulled into the lymphatic system. Your lymph capillaries are called blind capillaries because they don't have a heart pumping from this direction. They just stick into the tissue with big gaps that allow them to pull in large debris, dead cells, cancer cells, whatever you need to get out of the tissue can squeeze through these wide gaps here and work its way slowly back into your circulatory system. Here it is again. Lymph vessels. Everywhere you have arterioles and venules and capillary beds, you're going to have lymphatic vessels. If somebody doesn't have a lymphatic system that works at all, think of that 3 liters of plasma of fluid staying in your legs. Elephantiasis is a condition which destroys the lymphatic system's ability to remove fluid. Now, this woman isn't fat. You can see from her upper body, this is just retained fluid in her lower legs. And of course, the lymph moves through the lymph nodes. It comes in, encounters B and T cells like mad, and then it leaves after they've been filtered and processed to try to make sure they're safe for your body to deal with. As I said, a lot of lymph nodes in the groin, a lot of them in the armpits. You can't see here, but it moves slowly, gets up into the subclavian veins here. The subclavian, that means behind the collarbone, behind the collarbone, and it dumps it back into the venous system so that it can be transported largely through the liver, which processes a lot of this, a lot of your lipids, and helps filter out some of the products that you want to get rid of, puts it in the bile so you poop it out instead of keeping that in your blood. Two kinds of edema. Edema means fluid has gotten places you don't want it to. Okay? Edema happens when too much fluid leaves and not enough gets reabsorbed for one reason or another. You can have high blood pressure, hypertension. The filtration forces are too high compared to the absorption forces, and your ankles swell up. You can have a blockage of veins or the lymphatic system to make it hard for the fluid to leave the leg, and therefore the pressures build up and your ankles swell up. Pitting edema is the most common kind of edema, and this happens when you have excess fluid in the interstitial fluid because it filters out and you can't get it back. Now, the reason it's pitting is if you press on the swollen tissue, if you press on it, it'll leave a little hole there for a while before it fills back up because you're pushing the fluid out through those rivulets, out from under your finger, and it leaves a pit for a minute or a couple of minutes or 10 minutes, depends on how bad it is. Pitting edema is a good way to determine that it's normal edema from hypertension. Edema is never good, but this is the most typical kind. When I tore my ACL and I had knee surgery, and for a number of months afterward, I had pitting edema on my lower leg. Obviously, the surgery cut some veins, perhaps some lymphatic vessels and stuff, and before they regenerated, my calf was pretty swollen up. My shin was swollen. I could push on it, and it would leave quite a dent there. It was really gross. So, of course, I did it all the time because it was really kind of neat, too. Pitting edema. Non-pitting edema, often myxedema, it's a problem inside the cell. It's often a metabolic problem. It can be caused by hormonal problems or metabolic malfunctions of the cells. And the cells themselves swell up. Now, if you push on a cell that's swollen, it just springs back, and you don't get a pit out of it. It happens in the face, myxedema, causes your face to get swell up, but when you push on it, it doesn't leave a pit there. This non-pitting edema tells you that the excess fluid is inside the cells rather than in the interstitial fluid, and therefore it's a different kind of problem that you may have to deal with. Okay, now that pretty much ends the part of the lecture that's going to be on this first cardio test, and even on the first cardio lab practical. The second lab practical is set up now to be the endocrine system, but also all the circulatory system anatomy. So I left this on here because it's good information for you to have. Just some basics of the circulatory system. Arteries take oxygen and blood to the tissues, and veins bring it back. Now we're talking about the systemic system. In the pulmonary system, it takes deoxygenated blood to the lungs and brings oxygenated back to the heart. Okay? But arteries leave the heart, veins come back. And that's always. They're often named based on the body part. You could have the radial artery, the ulnar artery, the femoral artery, the tibial artery, because you already know where those body parts are. It makes it a lot easier to find these things. There's some that have their own names that you'll have to learn, but a lot of them is just remembering where your bones and muscles are. The gluteal, a gluteal nerve or gluteal artery or something like that would go to your butt. So, remembering your A and P1 anatomy is going to take you a long way in doing this. Here we have first of all, you have the aorta. Now, on this first test, you need to know the aorta, the aortic arch, a couple of these major things coming right off the heart, the vena cava. You need to know the coronary arteries. But we're going to do all this other stuff on the second one. So you don't need to learn those today. But here we have the femoral artery, the popliteal artery. Remember, that's behind the knee. Anterior tibial, posterior tibial. Start looking at these because these will become important for the second lab practical. And you'll do some top hat exercises and stuff looking at these. And the ones with the, that are highlighted in red are most likely to appear on the test. I will give you another list of blood vessels that you need to know before that second lab practical. Here we have the carotid arteries going up into the brain. We have vertebral arteries that are going to go down the vertebrae and supply your blood to your spinal cord and so forth. We have the internal carotid goes to the inside of your brain. The external carotid goes to the outside of your skull and your scalp. You get into your brain, and we're going to have the circle of Willis, this little circle that takes the blood around to different of the smaller blood vessels that will serve different parts of your brain. We'll have a chance to learn these, though, before that second lab practical, the ones going down your arm, here's the thoracic aorta is in your thorax, above the diaphragm. The abdominal aorta is below the diaphragm, and it's going to have arteries that go to your stomach, to your intestines, to your kidneys, to your liver, to your spleen. And they're called things like the renal arteries, because renal means kidneys. Hepatic artery goes to the liver. So you'll learn all of those in time for the second lab practical, not this first one. Same in the leg. So spend as much time, and then the veins all come back. Most of them have similar names. You're going to have a radial and ulnar, but there will be a few different veins. They're not identical, so you'll learn those. You can start looking at these when you have time, but these will not be on the first test or the first lab practical. The veins of the head and so forth. Okay, here's the veins, the veins, the veins. And so, here's a good first list of some arteries and veins to know that have their own names. And then the others are identified by their location, like the radial, ulnar, tibial, anterior tibial, posterior tibial, and the like. Don't spend a lot of time studying this stuff before the first test and the first lab practical, which are next week. Okay. Finished.